So this is Physics 2212, Lab 3. This was the Circuits Lab by Jackson Banger. So in our intro, some of the main goals of our lab was we're trying to understand the concepts of current and voltage in relation to resistors and capacitors and how the resistors and capacitors will affect those type of things. We're going to measure electric current and potential difference, and we're going to compare the times of charging and discharging a capacitor. So some of our results that we got, all of the resistors that we used were how they should be, 47 ohms and 100 ohms. And so we found that the sum of our potential differences is 0. And the times of charging and discharging the capacitor were pretty close, if not the same. So some of our models that we're going to use, Kirchhoff's voltage law, pretty simple. Some of the potential differences is 0. And the circuit we used in our lab is right here. So here's a photo of the lab. So our first part of the experiment, we used the circuit with two 1.5 volt batteries in series and two resistors. One is 47 ohms, the other is 100 ohms, and then two ammeters. And there's a picture of the circuit there. So our first part of the experiment, we measured I1 and I2 as seen here to both be 0.02 amps, which makes sense. It should be conserved as it passes through both the resistors. So potential differences for the batteries came at like 3 volts, and then our first resistor, the 47 ohm, got negative. The potential difference was negative 0.97 or 94 volts, and then our 100 ohm resistor is negative 2.06 volts. So some possible errors is like rounding calculation errors, imprecision in the ammeter readings. And then we have our potential versus position graph. So this will show the potential difference as you follow along through the circuit. So you can see it jumps with the batteries and goes down with the resistors until it hits the ammeter. So our part 2 is a different circuit. It's an RC circuit. So 2 batteries in series, and then a capacitor and a light bulb. And so we're going to measure the time it takes for the capacitor to be charged and discharged. And we're going to do that through watching the light bulb. So as the capacitor is charging, it flows through to the light bulb, and you'll see the light bulb turn on, and then it will slowly turn off. And when it turns off, that's when it's charged. And then we'll disconnect the battery and watch the light bulb to see when it discharges. So some of our measured values, it took 39.38 seconds to charge the capacitor. And then once the battery was disconnected, it took 36.93 seconds to discharge. So the times for both charging the capacitor and discharging were very close. However, like in theory, they would be the same. So we had some errors in measuring our times. So the what if question: what if you charge the capacitor with no resistor circuit? How quickly would our ideal model predict the capacitor to reach full charge? Ideally, it would reach full charge instantly because there's no resistor to slow down the current, so it should just do it immediately. However, in real life, there is a lot of resistance in wires, there's resistance in batteries, there's a resistance in the capacitor itself, and this causes it to not charge instantly. Much quicker without the resistor, however, not instant, like our ideal.